Hello everyone, this is lecture 14 and today we are going to talk about a series solution about a singular point. So first we'll take the definition of a singular point and then we'll calculate the possible series solution about that point. So singular point for a second order differential equation. Okay, so consider the second order differential equation in normal form, which is second derivative plus p function of x into first derivative plus q function of x into y is equal to 0, where px is a1 by a naught and qx is a2 by a naught. So this definition we have already talked about this in the previous lecture also. Now uh, if either this p function or the q function diverges at when x approaches x naught, then x naught is a singular point. Okay, so any point is said to be singular if at that point either p or the q diverges. Okay, say for example find the singular points of the differential equation, and we are considering two examples here. First this second order differential equation and this another second order differential equation. So in the first case, if I divide this equation by x into x minus 1, then I can find what is my px is 1 over x minus 1 and qx is 3 over x into x minus 1. Okay, so this is my px and qx. So clearly you can see that when x approaches 1, this px will be divergent, and when x approaches 1 or 0, this qx will be divergent. So x is equal to 0 and 1 are the singular points for this first differential equation. Similarly, in this second equation, p is x over x minus 1 into x minus 2 and q is x square over x minus 1 x minus 2. So again you can easily see that x is equal to 1 and x is equal to 2 are the 2 points where p and q both are diverging here, but it is sufficient to if either one of them is divergent. Okay, so if either p is divergent or q is divergent at any x, then x that point is singular point. Okay, so here 1 and x is equal to 2 are two singular points of this. Okay, now the singular points can also be classified as into two categories. One is called the regular singular point and other is the irregular singular point. So we'll take this definition now. Okay, so regular and irregular singular point. So consider the second order differential equation in normal form again. Okay, and let x is equal to x naught be a singular point. Okay, that simply means that either px or qx diverges at x equal to x naught. Okay, now in addition, if we calculate x minus x naught into p, where x naught is the singular point, so x minus x naught multiplied by p, where p is this function, and also x minus x naught square time q. Okay, so this q function and x minus x naught square. Okay, with p a linear factor and with q a quadratic factor. Okay, so and if they remain finite when x approaches x naught, okay, if the limit on this function and this function are finite, then this singular point x naught is a regular singular point, otherwise x naught is a irregular singular point. Okay, so if any of these limit diverges, then it becomes a irregular singular point. Okay, say for example find the regular and irregular singular points of the differential equation this. Okay, so again a second order differential equation, our p function is x over x minus 1 square x minus 2 and q function is x square over this factor. Okay, so here p is this, q is this. So immediately you know the singular points x is equal to 1 and x is equal to 2 are the singular point because they are diverging at these 2 points. Now to check whether these singular points are regular or irregular, what we need to calculate is for x is equal to 1, we need to calculate x minus 1 into p and x minus 1 square into q. Okay, and then take limit x tends to 1 and check whether this is diverging or not. So if I multiply this p with x minus 1, then 1 x minus 1 will cancel out, but there still will be 1 x minus 1 factor in the denominator. So x minus 1 into p will diverge when x approaches 1. Okay, so because of that x is equal to 1 is a irregular singular point. Okay, because this factor x minus 1 p diverges as x tends to 1 because of this x minus 1 in the denominator. Okay, now for the other point x is equal to 2, so again I will calculate x minus 2 into p. So this x minus 2 factor will cancel out, so this will give finite value, and x minus 2 whole square into q, so that will also give a finite value. Okay, so x minus 2 into p is this, and x minus 2 square q is this vector, and when x approaches 2, this will give a finite value of 2, and this will give a finite value of 0. Okay, so both are approaching and remain finite, so x is equal to is a regular singular point. Okay, so once you calculate singular point, it is important to note whether the point is regular or irregular, and based on that we can find the series solution of the differential equation. Okay, so now we will talk about how to calculate the series solution. Okay, so power series solution, and consider the second order differential equation of this form. Okay, so the power series solution, in the last lecture we already talked about how to find this series solution about an ordinary point. So today we are going to talk about the series solution about the regular singular points. Okay, and this method is well known as the method of Frobenius. So for this let x naught be a regular singular point of this differential equation. Okay, so let x equal to x naught be a regular singular point of the equation. Okay, so if you are given a differential equation, find the singular point and then the regular singular point, and once you know the regular singular point, then one of the solution of this differential equation can be expressed in this form, in this series solution. Okay, it is summation cn x minus x naught, where x naught is a regular singular point, whole raised to power n plus m, where m may be a positive, negative, integer or fraction. M is to be calculated, m is calculated during the process itself. Okay, and if you remember the the method in ordinary point, we had cn x minus x naught power n. Okay, the Taylor series. Okay, now we have this plus m factor, because it's a regular singular point. So very similar to that, but a new factor of plus m in the uh, power of x minus x naught comes into play. Okay, so the method we already know that we have to take two derivatives of this, substitute it here. Okay, but when we will substitute it here, uh, uh, we can solve that polynomial equation for all the constants c1, c0, c2, c3, so on. Okay, so substitute this and its derivative in the given differential equation, but we also need to calculate this m. Okay, so how to do that? So equate to 0 the coefficient of the lowest power of x. Okay, remember the what if you, when you expand this into, put substitute it here and expand it into series, then whatever is the lowest power of x, the coefficient of that, if we substitute that to 0. Okay, so that will be a quadratic equation in m, and we call it a indicial equation or characteristic equation. That will be a second degree polynomial quadratic equation. So we can solve that and we can calculate m. Okay, so it will give two roots of m, two values of m. Okay, and if we equate rest of the powers of x, then we can calculate all the constants c1, c2, c3, so on. Okay, all whatever constants are there. Okay, and the c naught is not calculated because c naught will go away with this indicial equation. Okay, so you need to calculate c1, c2, c3, and you will calculate these constants in terms of the c naught. Okay, and the complete solution now depends on the type of roots of the indicial equation. So there are two roots, two values of m, and based on these two values of m, we will have solutions for this differential equation. Okay. So this is what I said, that there will be two roots of indicial equation. So let m1 and m2 be the two roots. Okay, so this quadratic equation in m, when we solve it, so let m is equal to m1 be one root and m is equal to m2 be the second root. So based on this, there are three cases, the three ways in which we can write the solution. Okay, so we'll discuss one by one. So based on the two roots m1 and m2 of the indicial equation, we have the following cases for the solution. That case 1 or type 1, when the roots m1 and m2 of the indicial equation are distinct. Okay, and not differ by integer, their difference is not an integer, then the complete solution can be written as a linear combination of solutions at one root and solution at another root. Okay, then solution is calculated at first root m1 and solution is calculated at the second root m2, and then their linear combination is the complete solution. So this is one very simple case. Okay, the second case is when both roots are equal. Okay, so when two roots m1 m2 of the indicial equation are equal. Okay, if two roots are equal, then this solution and this solution will be same. Okay, so we cannot just plug m1 in to find one solution and m2 to find another solution, because they will give the same solution. But then the complete solution is that we calculate one solution at m1. Okay, and m1 is equal to m2. Okay, and the second solution is calculated from this first solution by taking derivative with respect to m and then plugging m as m1. Okay, so complete solution is a times solution at m is equal to m1 plus b times derivative of y with m and then plugging m equal to m1 in that. Okay, so this is case 2. The third case is when the roots of the initial equation are distinct but they differ by integer. Okay, the first case was do not differ by integer, and in the third case when the roots they are distinct but they differ by integer, that means their difference is a integer value. Okay, and in this case let the m1 is less than m2, the one of the root must be less than the second. Okay, if they are equal then type 2 will come into picture. So let m1 be less than m2 and the roots are such that they are distinct and they differ by integer. Okay, so what happen in this case is that some terms become infinite at the lower root m1. Okay, so whichever is the smaller root, at that root some of the term of the infinite series they become infinite. Okay, so to overcome this we put this c naught constant as k naught into m minus m1, where m1 is the lower root. Okay, so we put c naught as k naught into m minus m1, and once we substitute this, after that we can calculate y value or the solution at m is equal to m1 at the lower root plus the other as y derivative m at m is equal to m1, and their linear combination will be the complete solution. Okay, so these are the three cases. Okay, when the roots are distinct and do not differ by integer, then solutions are calculated separately at both roots and then their linear combination. If roots are equal, then the solution is calculated at one of the roots and then the derivative with m at that root. Okay, and their linear combination. If roots are distinct but differ by integer, then we have to plug in the constant c naught as k naught into m minus m1, where m1 is the smaller root, and then we calculate one of the solution at m is equal to m1 and the second solution as y derivative with m at m is equal to m1 and then their linear combination. Okay, so these are three types of solutions when we have a singular point as a regular singular point. Okay, and this method is the method of Frobenius. If the singular point is a irregular singular point, okay, then no series solution of the form above exists. Okay, so we cannot calculate the series solution. Okay, so you have to remember that only we can find the series solution by these methods if the singular point is a regular singular point. Okay, so now I take example for all three types of cases here, and first case I'm taking is type 1. Okay, so find the power series solution about x is equal to 0 for the differential equation. So given this second order differential equation, okay, so clearly you can check this, that x is equal to 0 is a singular point of this differential equation and it is a regular singular point. Okay, so x is equal to 0 is a regular singular point of the differential equation. So I'm not calculating that, you can check that easily by using the method. Okay, now the idea is that if it x equal to 0 is a regular singular point, then we can assume that one of the solutions can be written by Frobenius method in this form, that yx will be equal to summation cn x raised to power n plus m, because x naught is 0. Okay, this is the solution and x naught is 0, so x power n plus m, where c naught, c1, c2 are constants and m is also unknown number which we will calculate in the process. Okay, so first step is that we calculate the first derivative of this, second derivative of this, and then plug all these things here. Okay, So we calculate differentiate this with x to find that the first derivative x is n plus m cn x n plus m minus 1, and now we are not changing it n0 to n1 because n0 is not a 0 here, and when if you put n0 it is still m c0 x raised to m minus 1 because of this m. Okay, in ordinary when points are ordinary, this was x power n and it becomes ncn. In that case we change this series as n is equal to 1 to infinity, but in a singular case it is n0 to infinity itself because n0 is not making the term 0. Okay, at n0 still there is a non-zero term. Okay, similarly we calculate the second derivative. Okay, so second derivative means that n plus m minus 1 goes here into x raised to power n plus m minus 2. Okay, so this term, and then we substitute all these three back in the differential equation. Okay, so on substituting it is 2x square into second derivative, so 2x square into the series plus 2x square minus x into first derivative, so plus 2x square minus x into the first derivative series this, and plus y, and y is this series. Okay, and now we know the steps. The first step is that we take the x terms which are lying outside the series to inside the series. Okay, so x square goes inside here, similarly x square goes inside, this x goes inside, and it is sum, so we use linearity that this first factor times series minus second factor times series plus this is already having coefficient as a constant. Okay, so we rewrite this by taking x terms which are outside the series to inside the series. Okay, so that x square comes inside here, similarly x square comes and that minus x comes here and so on. Okay, now once we reach at this step, if you remember last lecture, we need to do two things. One is that the powers of x are to be made same and the starting positions are to be made same. Okay, so here x power is n plus m, here it is n plus m, here it is n plus m, here we need to also make it n plus m. Okay, so in the second series we will put n as n minus 1 everywhere to rewrite this second series, and first, third and fourth series are not changed, it remains that is it, so that the powers of x exponents are same. Okay, so we change n as n minus 1 in the second series here in this. Okay, so this say 2 times series, this n becomes n minus 1, so n plus m minus 1 cn minus 1, and it becomes x power n plus m minus 1 plus 1 goes off, and starting position when n is substituted as n minus 1, so n minus 1 equals 0 means n equals 1. Okay, and this first, third and fourth remain same. Now the exponents, the powers of x are same. Now we just need to make the starting position same, so at three places it is n0 and here it is n1, so everywhere we'll make n1 by putting n0 value. Okay, so n0 here and rest will be from n1, n0 value here, so rest will be from n1, n0 value will put here, so rest will be from n1. So when we put n0 here, then it will be m into m minus 1 c0 x raised to power m, 2 times this term will come outside. When we put n0 here, it will be minus m c naught x power m, and n0 here will be c naught x power m. So these three terms will come outside and rest terms will be from n is equal to 1. Okay, right, so this is n0 from here, and rest series becomes from n is equal to 1, the same series. Okay, this is already from n is equal to 1, so it remains as it is. This third n is equal to 0 we substitute to write minus m c naught x power m, and rest n is equal to 1 to infinity remains the same series, plus n is equal to 0 we substitute it, so c naught x power m comes outside, and plus n is equal to 1 to infinity, rest of the series remain here. Okay, now these terms of x power m we can combine. Okay, these three terms into a single term, and because the starting position and powers are same, so all these sub series we can combine into a single series. Okay, so this 2m into m minus 1 c naught x power m outside, and similarly it is minus m and plus 1 from here. Okay, so this is a quadratic equation with multiplied with c naught x power m, and we combined this second series, third series and fourth series because they contain cn x power n plus m. okay, to write this. And this second series, the constant is cn minus 1, so we kept it here. And this can be further combined, okay. So this quadratic term, it is 2m square minus 2m minus m, so it is minus 3m plus 1, okay. This terms are again combined, and this also brought inside this summation to rewrite into this form, okay. So n plus m minus 1 is common from here and also from here, so that went outside. And 2n plus 2m minus 1 cn and plus 2 times cn minus 1, this, okay. So once you reach here, then the lowest power of x is x power m, okay, because when n is 1 it will be x power m plus 1, n is 2 x power m plus 2, and so on, okay. So this is the lowest power of x, which is x power m. The coefficient of this, if we put it equal to 0, this is the indicial equation, or also called the characteristic equation, and it will give us two values of m, okay. So we will not make c naught 0, we'll keep c naught non-zero and put this 2m square minus 3m plus 1 equal to 0 to calculate two values of m from here. And rest of the coefficients of x are this. So if we put this equal to 0, we can calculate cn's in terms of lower constants, okay. So first we'll put this equal to 0 and then this equal to 0, okay. So by equating the coefficient of lowest power of x, that means coefficient of x power m, the initial equation is this 2m square minus 3m plus 1 equal to 0, and this will give two roots. So two values of m which satisfy this is m value 1 and m value half, okay. So the roots are distinct and they do not differ by integer, their difference is not an integer, okay. So it's a type 1 question, okay. Roots are distinct and do not differ by integer, okay. So once you know this, okay, so keep it in record that your it's a type 1 question. That means the final solution will be based on solution of first root plus solution on second root, okay. So now we need to calculate all the constants, and for that we substitute all the coefficients of x to 0. So that means this 2n plus 2m minus 1 cn plus 2 cn minus 1 equal to 0. So this is the coefficient inside the summation with, because series was starting from n is equal to 1 to infinity, so this is true for all n greater than equal to 1. So from here we can calculate cn in terms of cn minus 1, okay. And then we can plug n value 1, n value 2, n value 3 to calculate c1, c2, c3 and so on, okay. So if we put n value 1 here, then c1 is calculated as this. Then we put n value 2 to calculate c2 in terms of c1, and because c1 is known, so we can calculate c2 in terms of c0. Then when we put n is equal to 3, so we will get c3 in terms of c2, and because c2 is known, we get c3 in terms of c0 by substituting this value here, okay. So in this way we can calculate, so on we can calculate all the constants. So c1 in terms of c0, c2 in terms of c0, c3, okay. So now our solution was summation cn x raised to power n plus m. So we'll substitute all these constants there, c1, c2, c3, so on, okay. So our assumed solution was summation cn x power n plus m. So if we open this, it is c0 x power m plus c1 x power m plus 1 plus c2 this. So we will plug c1, c2, c3, all these constants values we calculated. c0 we have not calculated, remember, okay. So once we plug c1 in terms of c0, c2 in terms of c0, c3 in terms of c0, then c0 will go outside. Similarly x power m goes outside, and rest is whatever constant values we calculated, and this is a series, okay. So now we know that we have two roots of m, and those roots are distinct and do not differ by integer, okay. So will calculate one solution at first root and the other solution at second root, okay. So for m is equal to 1, okay, the one solution, okay, y at m is equal to 1, so we just put m is equal to 1 here in this series and we find one solution, okay. Similarly, the other root was m is equal to half, so we just plug m is equal to half in this series and we get the second solution at m is equal to half, okay. And the complete solution is a linear combination of these two solutions. So complete solution is a constant times first solution plus constant times this second solution, okay. So this is how you calculate a series solution for type 1 problem where initial equation roots are distinct and do not differ by integer. Okay, now we take one example from the second type. Okay, where initial equation roots are equal. Okay, so we'll see, say for example, this is the differential equation x into 1 minus x second derivative plus 1 minus x first derivative minus y equal to 0, and we have to find the power series about x is equal to 0. So we have to check what type of point it is. Okay, so if you check x equal to 0, so you'll find that x is equal to 0 is a regular singular point. Okay, so I'm not calculating this again. So x equal to 0 is a singular point and it is a regular singular point. If that is true, then the power series solution we can assume in this form. Okay, so we have talked about this a lot of times now, that we assume series solution as summation cn x power n plus m whenever we have a regular singular point origin. Okay, and then we calculate one derivative of this and second derivative of this and plug all those in the given differential equation. So these steps, okay, so these steps are similar, and we plug all these back here. So x into 1 minus x into second derivative, x into 1 minus x into second derivative, plus 1 minus x, this 1 minus x into first derivative, so first derivative is this series, and minus y, so minus of this series. Okay, here, and then if you remember steps, that we take whatever x are outside summation, we bring them inside the summation. So x minus x square, we can write this, so x my goes inside and then minus x square goes inside here. It's one time series minus x time series and minus, so there are 5 series here. Okay, so I'll just rewrite them. So that's x times series and then minus of x square times series, so x square goes inside here, plus 1 time series minus x time series and minus y, okay, equal to 0. And then uh, two steps, that the power of x needs to be same and the starting position needs to be same. So first the power of x needs to be same everywhere. Okay, so we'll uh, change the power. Okay, so if I have to change it here, then I have to put n as n plus 1 to make it n plus m, and in that case it will be n plus 1 equal to 0, so n will start from minus 1. Okay, so I'm not doing this, I'm changing this power to n plus m minus 1. Okay, so that if I put n as n minus 1 here, so it will be n plus m minus 1, and then this will be n starting from 1 to infinity. Okay, similarly in all these. So instead of changing in these two, I am changing in these three by putting n as n minus 1 in these three series. Okay, so you can do it from here also and make it n minus 1, it is okay with that. So okay, before we do that, we can also do this, that we can combine these two terms because the starting position is same and the power is same. So these two can be combined into a single series, and similarly these three can be combined into a single series because the starting position is origin and power is x power n plus m in all these three. So these three series can be clubbed into a single series. Now because we need to make the power same, so I am changing this as n to n minus 1, so that it become n equal to 1 to infinity, and here it is n plus m minus 1, here it will become n plus m minus 1 whole square plus 1. Okay, so we change, this term is not changed, and this term we change to this new by shifting n to n minus 1. Okay, now the starting position need to be same, so we put n is equal to 0 here, and then starting position will be same, n is equal to 1. Okay, so when we put n is equal to 0 here, so it becomes m square c naught x power m minus 1, and then starting position becomes same, n is equal to 1 to infinity for both of these. So these two can also be combined now, okay, into a single series. And once we do this, then the initial equation is written from the coefficient of lowest power of x, and the coefficient of lowest power of x is this here, x power m minus 1, and the coefficient is m square c naught. So m square c naught equal to 0, and because we are saying that c naught we will take non-zero, so m square equal to 0, and we'll calculate two roots of m will be 0 0. Okay, so we have two equal roots 0 0 here, and then we'll put this equal to 0, the coefficient of x from here, and from here we'll calculate cn. Okay, so first the coefficient of lowest power of x, the initial equation, which gives two roots m0 0, and then the coefficients of x from the higher power or the from the series, and series was starting from n1, so n equal to 1 to infinity, so n greater than equal to 1. From here we calculate Cn, okay, and then we plug n as 1 2 3 to find c1 c2 c3. Okay, so this process is same, right? C1 we calculate it from here in terms of c0, then n2, so c2 in terms of c1, and c1 is known, so c2 in terms of c0, and so on similarly. Okay, so on, and then we plug all these constants back in the solution that we assumed. So once we plug c1 c2 c3 all values here, then we can write this solution as this is the infinite solution. Okay, now the value of m, now it's a double root, m is equal to 0 0 or equal root, and if roots are equal, then one of the solution is calculated at the root. So at m is equal to 0 we can calculate one root. Okay, so at m is equal to 0 the solution is one solution y1, say. So we just plug m value 0 here and we find one solution. The second solution cannot be calculated using m0 because it will come out to be same. So the second solution is that we differentiate this y function with respect to m, okay, not x, with respect to m, and then we put m0. Okay, so that calculation I am leaving, just you need to calculate y derivative with m here and then plug m is equal to 0 in that. Okay, so that will give you this result. Okay, here it's a product rule. Okay, so the outside the bracket there is 1m and inside the bracket there is a 1m. Okay, so this whole series multiplied with derivative of this, so that will be something x power m, derivative with m will be x power m into log x. Okay, so x power m into this is nothing but the y1. Okay, so whatever y1 will come with log x, this term is easy to calculate. The second is x power m times derivative of this series, which is this part. Okay, so you need to calculate the derivative of this, you will get this result. Okay, after plugging m is equal to 0, and the complete solution is the linear combination rule. So a constant a times y1 plus constant b times y2. Okay, so that's how you get the general solution, y as a times y1, a times this series plus b times this whole series. Okay, so this is type 2 question. And now take one more example, the type 3 question, where the indicial equation roots uh, are distinct but they differ by an integer. Okay, so say we take this example that find the power series solution about x is equal to 0 for the differential equation. This, okay, again second order differential equation. So again x is equal to 0 you can check is a regular singular point. Okay, so x equal to 0 is a regular singular point, and again for x is equal to 0 to be regular singular point we can use Frobenius method and assume solution of this form. Okay, and then we take one derivative and second derivative of this and then plug them back here. Okay, so these steps are just the same. Okay, first derivative, second derivative, plug all these back here. Okay, so it is x times second derivative, so x times the series, plus 2 times first derivative, so plus 2 times the series value from first derivative, and minus y, so minus y. Okay, then take this x inside here, so it will become x power n plus m minus 1. Okay, it is already constant, it is already constant outside. Okay, so you just need to take one x here inside this series. Okay, so this term, so this power changes here. Okay, then uh, you can combine these two. Okay, easily, because the starting position is same and the power is same, and because this power is different, so keep this as separately. Okay, so these two, n plus m is common, and then n plus m minus 1 plus 2, so that is n plus m plus 1. Okay, so when we combine these two, this series will become, then we need to make the power of these two same. Okay, so in the second we will put n as n minus 1. Okay, so it will be n 1 to infinity cn minus 1 x is to n plus m minus 1. Okay, so this term and this first remains same. Okay, and to make the starting position same now, okay, we put n equal to 0 here, so that rest of the series will start from 1. So when n is 0 it will be m plus 1 into m into c naught x power m minus 1. Okay, so this will come outside. Okay, n0 means m into m plus 1 c naught x power m minus 1, and rest n is equal to 1 to infinity the same series, and n is equal to 1 to infinity this series. Now these two can be combined into a single structure. Okay, single series. Okay, So this minus Cn minus 1 into xn power n plus m minus 1. And so the initial equation is m into m plus 1 equal to 0, which will give two values of m as 0 and m as minus 1. Okay, so they are distinct but their difference is integer. Okay, and then we can put this coefficient 0 with n greater than equal to 1, and we calculate Cn in terms of Cn minus 1. Okay, so initial equation is m into m plus 1 0, which give two roots 0 and minus 1. Okay, and equating coefficient of other powers of x, we can calculate this Cn, and from here with n is equal to 1 2 3, we can calculate C1 C2 C3. Okay, C1 C2 C3 and so on, other constants in terms of C naught. And then as we said, we will first write the solution y, which we assumed, and we'll plug C1 C2 C3 there, as we are doing in all examples. Okay, so in this solution we plug C1 C2 C3 so on. Okay, so this is the series solution yx, where m are integers, m are distinct and they differ by integer. Okay, so when m's are distinct and they differ by integer, whichever is the lower root. Okay, in this case remember the roots are minus 1 and 0 with integer difference, and lower root is minus 1. Okay, so and you can check that at the lower root some of the terms become infinite. So if you put it here, then see in the denominator it becomes 0. Okay, so some of the terms will become infinite. Okay, so what we do is we substitute the constant C naught as k naught times m minus that root. So m minus that root means m minus into minus 1, so it becomes m plus 1. Okay, so we put C naught as k naught times m plus 1, so that we substitute this in this equation first. Okay, so when we substitute it here, so C naught will become k naught into m plus 1, that m plus 1 goes inside, so 1 time m plus 1 is m plus 1, and everywhere m plus 1 cancels out. Okay, when this m plus 1 goes inside. Okay, so here now this equation do not become no term becomes infinite when we substitute this root. Okay, so the first root is calculated by substituting m is equal to minus 1 in this equation. Okay, so if we one of the solution at m is equal to minus 1 is that we put m value minus 1 in this here. Okay, so if you put m is equal to minus 1 here, this will be 1 by x, this term constant is 0, this will be simply x, so 1 by x into x will be 1, which is this. Okay, similarly this will be x square, and then 1 by x is outside, so that will be x term with whatever value from here, which is half. Similarly here. Okay, so one of the solution is calculated by putting that lower root m is equal to minus 1 in this equation. After substitution, C naught is equal to k naught times m minus m1, the lower root, m plus 1 here. Okay, and for the second solution we take derivative of this y with respect to m. Okay, not x, with respect to m, and then plug m is equal to minus 1. Okay, so a derivative of y with respect to m and then plug m as minus 1. So I'm not solving, we can solve and check, this will be the solution. Okay, and the complete solution is again a constant time this plus a constant time this. Okay, constant time first solution plus constant time second solution. Okay, the other solution is a times y1 first solution plus b times y2 the second solution. Okay, so this is how you solve for series solution about a regular singular point. Okay, so in this the result on initial equation, characteristic equation that we were calculating for roots of m. Okay, so by series solution we were calculating this. Now we can also calculate it directly from the differential equation, just to show you that how to do that, and you can compare with the previous example that this satisfies. Okay, so let x equal to x naught be a regular singular point of the equation, this differential equation. Okay, so if x equal to x naught is a regular singular point, then this limit and this limit must be finite because it's a regular singular point. Okay, that's what we said for the definition of regular singular point, that the limit x tends to x naught, x minus x naught px must be finite, and limit x tends to x naught, x minus x naught square qx must be finite. And let p naught be the value of this limit and q naught be the value of this limit. Then the initial equation of this differential equation, which is obtained by series as the coefficient of lowest power of x. Okay, that equation is can be written as this: m square plus P naught minus 1 times M plus Q naught equal to 0, where P naught and Q naught are the values of limit from here. Okay. I'll just show you, this is the first example we did today, the type 1 question. Okay, in this case the x is equal to 0 is a regular singular point, and px is 2x square minus x by 2x square, and qx is 1 over 2x square. Okay, so if you calculate limit x tends to 0 on x p x and limit x tends to 0 on x square q, so limit x tends to x naught, that means limit x tends to 0 on xp is x times this p, and when you put x is equal to 0 here, you will find that the value is minus half. Okay, this 2x square will cancel out, so it is x minus 1 by 2. Okay, so it is minus half, and limit x tends to 0 or at x square q is when you put x tends to 0, x square into 1 by 2 x square q value, so it is half. Okay, so if you put p value and this limit value as p naught, this value as q naught in this equation, you will find the indicial equation. Okay, as 2m square minus 3m plus 1 is equal to 0. Okay, you can check on substituting this in this equation that this equation holds, and this is exactly the same indicial equation that we found in type 1 example that we did today. Okay, similarly you can check the examples type 2 and type 3 that we did today, that if you use this method and find the indicial equation, it is same as calculated by series. Okay, this is just a small check that what you calculated is correct. Okay, so this is it for today. In the next lecture we will talk about series solution for Bessel's equation. Have a very good day.